All right, so we learned what the chain rule was. Now it's time to use it, right? Unpack boxes. So or peeling an onion. Let's take a look at those ones that we couldn't do. Example one, right? The derivative with respect to x of the square root of, it's more than just plain old x, right? It's a function of x. So what we're going to do is what we would do if this were just a plain old x. We would rewrite any radical as a fractional exponent. And again, because it's in the verb format, we need to make sure that we bring down the d dx as well. So let me charge my Apple Pencil or sync it up. Notation, notation, notation. So d dx of, and we can get rid of the brackets here if we want, because we have parentheses now, okay? Now, when you walk up to the problem, right, it's going to be important, especially when we start going backwards, anti-differentiating, to identify the layers. So the outside layer is basically what you first encounter when you walk up to it, right? So it's like blob to the 1/2 power. I say blob a lot, right? Blob to the 1/2 power. So when we take the derivative, that's the layer we do first. So by the power rule, right, that's going to be 1/2 times blob to the negative 1/2, right? If that were just x to the 1/2, it would be 1/2 x to the negative 1/2. Yes, yes. Now we don't unpack both boxes at one time, right? So this is still x squared minus 1. Now I put times, and now I look inside and I'm like, oh, there's something in there. It's x squared minus 1. So I multiply by its derivative. What's the derivative of x squared minus 1? 2x. Boom. Okay. Minus 0 or 2x. And that's it. That's the derivative, right? There were two layers. You had the blue layer and the purple layer. And now we have two links in our chain. We have the first one, which is bigger, right? This is big. And then the next one is small, just like the Russian nesting dolls, right? As you continue to take subsequent derivatives, those other factors should get smaller and smaller. Now all we have to do is possibly clean it up, right? So we can do that. The 2 and the 1/2 will divide out, and that leaves us an x in the numerator. The big factor is to the negative 1/2, so that jumps back down into the denominator under the square root. And there it is. That is the derivative of the square root of x squared minus 1. Okay. Sometimes I call it peeling an onion too, right? You can only peel an onion one layer at a time. Unpacking the boxes, whatever you want to call it. Chain rule. Chain rule. Now, let's see what this would look like in Leibniz form, okay? In Leibniz form, I'm going to say let f of x equal the square root of x squared minus 1. And let's let g of x actually, let's do this. Let's let g of x equal the square root of x, and let h of x equal x squared minus 1. So what do we know then? We know then that f is really, or I'm sorry, f of x is really the h function plugged in for g. So g of h of x, right? That's all it is. So what I could do if I wanted to figure out what the derivative was is take the derivative of one and multiply by the other. I don't want to do this yet. Let's not do that. Let's wait until we have it in equation format. Okay. Leibniz notation is great, but in this case, function notation is a little bit easier. Let's get a few under our belt before I do that. Okay. All right. Let's look at letter B then. This derivative with respect to x of not just sine of x, is it? It's sine of 5x. So anytime you have an inside function that's more than plain old x, it's going to be the chain rule. Parentheses are your best friends in this class, right? Better to have them and not need them than need them and not have them. And adding them here around an inside function can help you. So the outside layer is now sine of blob, and the inside layer is the blob, which in this case is 5x. How many layers do we have? 2. How many links in our chain should we have? What do I mean by links in the chain? I mean factors, okay? So we should have 2. It's a good way to keep inventory. So here we go. Nothing needs to be rewritten. I added parentheses. What's the derivative of sine of blob? Cosine of the blob. And remember, the blob goes in there. We don't take the derivative of 5x right now and call that cosine of 5. One layer at a time. Times, and now we say, okay, times the derivative of the next layer. What's the derivative of 5x? 5. Yeah, there it is. That's the answer. So how would we clean that up? Well, maybe put the 5 in the front, right? 5 cosine of 5x. And I guess you don't even need the parentheses anymore. It's understood. That's it. Nothing to it. So A, B, C, you do C. You do C on your own. Okay. On your mark, it said go. I'm going to do it on my own, and we'll see who finishes first. Are y'all done? When the only tool you have is a hammer, you have to make everything look like a nail. I only know the power rule. I only know the power rule. So I have to expand this out completely so that I can use the power rule. So here's one of them times another one. That's 2. And then here's that times another. So I'm up to, this is 3x minus 2 cubed. I got to do this 4 more times, and then I can take the derivative. Yucky, yucky, gross, gross. Bad, yeah. Hey, let's take the derivative using the chain rule. We have blob to the 7th, and then we have the blob itself. So 2 layers, right? With 2 layers, we should have 2 links in our chain. We work from the outside in. Blob to the 7th by the power rule is 7, blob to the 6th. What goes inside the parentheses? 3x minus 2. Okay, times, here's the next link in the chain, times the derivative of 3x minus 2 is 3. There you go, 2 links in the chain. I'm done with the derivative. All I got to do is clean it up, which is going to be 21 times 3x minus 2 to the 6th. Notice I'm done with the derivative before that other guy is really even done cleaning up 3x minus 2 squared. Wow. Well, cube. He knows square multiplied over square. No. Once we take the derivative, the ddx is gone. Okay. If we do any rewriting like we did on the first one, it still needs to be there. Okay. All right. Letter D, let's do this one together. I got 2 terms. It's only the second term that has a composite function in it, right? Because it's not tangent of x, it's tangent of x squared. So here we go. The derivative of x is 1. There's the first term. Minus, now the outside layer on the second term is tangent of blob. What's the derivative of tangent of blob? Secant squared of the same blob. Times, on that term only, the derivative of x squared, which is 2x. Yeah. That 2x does not get multiplied by both terms, by the 1. You have to unpack the boxes as you get to them. So it's only that second term. So if you clean this up, this is 1 minus 2x secant squared of x squared. There you go. Kaboom, right? Chain rule. It's fun. It's easy. It's been easy. All right. Now, what the heck is this doing in the chain rule section? Isn't this just a Hody high minus Heidi ho over ho ho? No, it can. No, it is. It is. It is. You could do Hody high minus Heidi ho over ho ho. When you do that, though, what is d high? What's the derivative of the high function? 0. 0. You could do Hody high minus Heidi ho over ho ho. It works. But I put this in the chain rule section because look, for problems like this, when you have a constant in the numerator, it might be faster, especially if we're taking multiple derivatives, to bring the quantity that's in the denominator into the numerator. Okay. Now it would have to be a chain rule because I don't know how to expand x plus 1 to the negative first, right? So this would be blob to the negative first. What would be the derivative of blob to the negative first? Negative blob to the negative second, right? And then times the derivative of the blob. What's the derivative of x plus 1? Just 1. Yeah. So now if you clean this up, you get a negative 1 all over x plus 1 squared. That's the same thing you would get if you did Hody high minus Heidi ho over ho ho. But you got to remember that d high would be 0. And you just have another option now. When you have a quotient like this and the numerator is just a constant, especially if we wanted the second derivative, it's going to be a lot faster, I think, if you just bring it to the top, use the chain rule, and then clean it back up. So you have an option. We have more tools than just a hammer. All right. Let's look at F. It's sine squared of 3x. Goodness gracious. How many layers do y'all see on that one? I see 3 layers also as well. Okay. So what we're going to do is we're going to rewrite it to help ourselves see the layers. We're going to add parentheses around the 3x, but we're also going to unpack the sine squared. Remember, that's the condensed form. So when we're rewriting it, we keep the ddx in place. All right. So what's going to be the outer layer, the outermost layer? Not sine. Blob squared. Yeah, blob squared. Yeah, I know that's what you meant. And then inside there we get sine of, just like when I said Brandon, I meant Braden. I'll never forget that or forgive myself. There you go. Do y'all see the layers there? We got the red layer, which is the blob squared, the green layer, which is the sine of blob, and then the beefy brown layer, which is the inside layer 3x. With 3 layers embedded, guess how many links in our chain we're going to have, or how many factors we're going to have? 3. Okay, it's a good way to keep inventory. And it's nice to color code it too. So notice the ddx is also still in front, but now we're ready to go. So blob squared becomes 2 blob to the first. And what goes inside the parentheses? Do I put cosine of x in there right now? Right. I just rewrite it. Yeah. You don't want to get crazy and start taking the derivative of more than 1 layer at a time. Times. Now we move on to the green layer. The derivative of sine of blob is cosine of blob. No, you don't have to say to the first power. I do that for inventory reconciling purposes. I want to make sure that I've considered it and not just forgot it. And then times the derivative of 3x, which is 3. So there you go. Red factor, green factor, brown factor. 3 layers, 3 factors. Like the Russian nesting dolls, each factor gets smaller as you go from left to right. Okay. And now if you were to clean it up, there's a couple ways you could do it. The obvious way, since it's to the first power, is just to combine the 2 and the 3 and get 6 sine of 3x cosine of 3x. All right, that's one way to do it. But there is another way to do it using a double angle identity. Do y'all remember? Remember off to the side here, 2 sine of x cosine of x is equal to sine of 2x. Or how about this? 2 sine of blob cosine of blob is equal to sine of 2 blob. Don't I have that in highlighted yellow? 2 sine of 3x cosine of 3x. Yeah. So the highlighted part should become sine of what? 6x. Good. And then I still have the 3 in front. Yep. That's the double angle identity for sine. It might happen, multiple choice answer, right? I doubt it, but you know, maybe later when we want to set this equal to 0 or something, maybe it's easier to solve sine of 6x instead of 2 different variable factors. All right, chain rule, chain rule. Okay, so far so good? Yeah, all right, let's move to letter G. Letter G. We can now combine the chain rule with other rules, like you walk up to this problem, it's the derivative with respect to x of x, a variable, times secant of a variable. So what rule out of the box are we going to use here? Product rule. Good. You have a variable function times a variable function. It's product rule first. Now remember, for the product rule, there's a way to take inventory as well. You'll have as many terms as you have factors. So here we have 2 factors. We should end up with 2 terms. And we only take the derivative of 1 factor per term. Yes, yes? Yes, yes. So here we go. The derivative of the first factor, I do first. The derivative of x is 1 times the second factor just goes along for the ride. We just rewrite it. Close, close. Parentheses all over the place, okay? And then plus, now the x factor gets rewritten. And now it's time for the derivative of the second factor, which, oh, the second factor is secant of blob. So that's going to be a chain rule. This is a chain rule inside of a product rule. So let's see, what would be the derivative of secant of blob? Secant blob, tangent blob. The derivative of secant is secant tangent, and it's got to be the same blob. Yeah. No, that's fine. Yeah, secant tangent is the same as tangent secant. But it's the same blob. They both get the blob. Okay. The derivative of secant of blob is secant blob tangent blob times the chain rule, right? It's got its own inside function. So parentheses, what's the derivative of x squared plus x plus 1? 2x plus 1. Boom. And then boom. Notice we don't multiply by 2x plus 1 twice, because we're not taking the derivative of what we're creating. We're taking the derivative of the original problem. So sometimes I might actually do something like this, you know, just to show you where the 2x plus 1 came from. But it's not really coming from the x squared plus x plus 1 that's on the same row as it. It's coming from the one that's way up here in the beginning. Okay, so we don't multiply by twice. There you go. So we do have 2 terms, right? Got it. And then that second factor has 2 layers. So it has 2 factors, the red factor and the blue factor. And then we'll save the cleanup for like another day. All right. You could factor out a secant blob though, if you wanted. Okay. Yeah. I'm going to skip H because I don't even think H is defined, and I don't even like it. Okay, I don't like it. It ends up being kind of funky. Let's do this one though. Let's do this one. You walk up to this problem, and you're like, "What's up, blob squared?" So this is a chain rule. Okay. So let's go ahead and do that. You can kind of pretend that you don't see what's on the inside. It's just blob squared. When you take the derivative, then you get 2 blob to the first. And remember, the blob just gets rewritten. There's the first layer. Times. Now you go inside and you're like, what's up, quotient? So now the next link in the chain, the next factor is going to be the Ho-D-High rule. Yes? So Ho D high is 3, Ho-D-High minus high. D ho is 2x all over ho ho x squared plus 3 squared. Okay. This is a quotient rule inside of a chain rule. And then we'll clean that up some other day. Okay. That's a great place to stop because we finished example 1. Chain rule. Chain rule will get so much easier because it's all over the place. It's pretty prevalent. Yeah. All right. Have a great weekend. We'll see you all at the game tonight. The worksheet for 2.5 is due Tuesday. Take your time with particle motion. Bye-bye.